This video is about decidability and what it actually means that something is decidable. Decidability. This MOOC actually deals a lot with the question, what can be done using computers? What problems can we actually solve using computers? And to this end, we need a more formal definition of what's actually decidability. What does it mean? The framework we usually use here is that we encode our problems into languages, into language problems, more specifically into the membership problem of a language. So what we do here is we encode our problems, and the problems we consider here are always yes-no problems. And we encode them into membership problems. Membership problems for specific languages. The advantage is that we get a unified framework for it. How does it work? Instead of checking whether a Turing machine M, for example, holds on input X, we consider the question, we encode it into the membership problem, whether some string W #X, that's just a separator, whether this string is in some specific language H, where we define where H is actually the set of all encodings of Turing machines separated by inputs, such that the Turing machine corresponding to the encoding W holds on input X. So all our problems will be encoded into language problems in general. Now we define what it actually means that a language is decidable. And the definition is a language L is decidable. Decidable meaning we want to decide whether some X is in L, or recursive, which is another word for the same idea, recursive. And there are two possible definitions. The first one is if there is a Turing machine M that computes on input X, 1, if X is in L, that's the language that's supposed to be decidable, and 0 if X is not in L. That's the first possible definition of decidability. The second one is if there is a Turing machine M, that on input X holds in accepting state if X is in L, and holds in non-accepting state if X is not in L. what do these two definitions have in common? And the common ground for both definitions is that the Turing machine must always hold. The Turing machine holds for both cases, so for both cases. And that's the important point. The Turing machine is not allowed to not hold, not stop. Okay, how does it look like? First idea is, of course, we have on the tape, we have the input x1 to xn of x, and in the first case, if the word is in the language, then we should either have a Turing machine that does the following: changes the tape such that we have a 1 on the tape. That's the first possibility. The second possibility is, if it's not in the language, then we should have on the tape a 0. That's this part here, computing function. Alternative, if it is in the language, then we should end in an accepting state, and if it is not in the language, then we must end in some non-accepting state. So this here is the case that x is in L, and this is x is not in L. So both definitions are in fact equal, because, for example, if we have a Turing machine that will at some point stop, then we can actually check whether we have a 1 or a 0 on the tape, and if we have a 1, we can go to an accepting state. If we have a 0, we go to a non-accepting state. So we could come from a Turing machine using the first definition to a Turing machine for the second definition, and vice versa. If we have a Turing machine that uses the second definition, if we're in an accepting state, we can simply erase the tape and write a 1. And if it's a non-accepting state, we just erase the tape and write a 0. So then we could come from this Turing machine to this Turing machine. So we see that they're in fact both equivalent. Important thing to remember is that for decidability, we actually need a Turing machine that holds independent whether the word is in the language or not.